Okay guys, in terms of example, I will discuss in different slide. So we have stopped here previously. So we continue from here in terms of lecture. And we continue with the parallel operation of a AC generator. Okay, we have a generator whereby usually the normal generator that we put at site for the currently technology, most of it are the synchronous generator, which the generator itself can produce the frequency of our transmission line voltage spec of 50 or 60 Hz of frequency. Means whatever we generate from generator, from the prime mover, usually prime mover is taking the force from the turbine. Maybe for the generator that produce 50 or 60 Hz, the turbine came from the source of hydro, wind, and etc. Engine, diesel engine, gas turbine, and we deliver three-phase output to the grid. Okay, for the time being, if the generator to operate on its own by right or it's operate alone, so there will be no issues. So whatever produced voltage, current and frequency being produced by the generator will be consumed by the load. But what happens if the generator to be need to be parallel or combined together, such that it can cover a heavier or bigger load? And so instead of here, the real P, real power and reactive power Q supplied by generator is fixed, and each generator will have their own rating. Means it can produce up to the certain P and Q. So this is constraint of the power demand by the load lah. So whatever the load needs, so it depends on the generator. So that's the, let's say you are buying the 2 horsepower of generator or 2 kilowatts of generator, so that's the rating. So you cannot connect more load. You connect more loads, the voltage will drop, current will drop, and the frequency will amended. The frequency and terminal voltage varied by the governor set points of the field current. So we have the field current field circuit, and we have the main circuit. So the field circuit will control how much the terminal voltage and the current that can be provided by the generator. Isolated synchronous generator supplying its own load independently is very rare. So means that the generator which operate alone is very rare. Means that if you have synchronous generator, you have to parallel most of them in parallel mode. Because what happens if no generator or some of the generator, they need periodic maintenance. Maybe after 13 years you need to shut down and service. So if you have only one generator, so it's a problem. If you have multiple generator, you can shut down a few of it and still operate from the other branch. All generators are driven by prime mover in terms of a mechanical source, power source to the prime mover, and the generator will generate current, voltage to the load. Okay, synchronization. Why we need synchronization is that we, by right in practical, we have multiple generator put at one side, then we supply to the grid, and the grid will distribute to the load and housing areas, industrial, manufacturing sites, construction site. Means that a few generator places around the, let's say in Malaysia Peninsula, and will be combined together into the grid, and the grid will supply to the load and all over the peninsula. Okay, means that it can supply a bigger load compared by one mechanical machine or generator itself. So it can increase in terms of their reliability in power system, since that the failure of one unit will not cause any harm to the total grid issues. So it allows also one or more of them to be removed or shut down. So for preventive maintenance, because we are not expect the motor to be damaged first, then we repair. So it's better to service and such that it can perform the best of it and throughout their service life. Maybe designed for 50 years, so throughout 50 years it will not suddenly break down in the field, but we do predict maintenance such that the machine can perform and better. So if only one generator is used, it's not operating near full load, so the machine will be relatively efficient. For generator or for synchronous generator, it is preferable to operate at near full load. And you have generator, you operate in 10%, 40% of the full load, so it's not efficient. The efficiency is very low. For synchronous generator, the efficiency will be very high or at top. Best performance of it when you operate near the full load condition. So you have to, means that if you want use one machine, use at near full load. If you need to add up some more machine, you have to make sure that the two machines to be operate at full load. You cannot have, let's say, 5 machines, all of it operate at 10%. No. If you need, you have a load which can cover by 2 machines at full load, so you run only 2 machines. Another 3 machines, you keep them shut down and shut down. You only on when the load required. So it is possible to operate only possible to operate only fraction of them. Means that you just operate 2 out of 5, 1 out of 5, and with the near full load condition. So the slide or the YouTube link here will show you in terms of how the generator will be parallel before connect to the bus bar. Okay, the rules and the condition before synchronization or before you parallel all the machine. So the RMS voltage, if let's say you want to parallel 2 generator, must be equal. So the RMS line voltage, the line voltage must be equal. Let's say you have one generator at higher voltage, another one generator at lower voltage. What happens that the higher voltage generator will supply your lower voltage generator. Instead of it supplies to the grid, it will charge, just like a battery. You have a higher voltage of a battery, it will charge the lower voltage battery instead of supply to the grid. So that is the issue. And the 2 generator must have the same phase, also the same. If you have different phase, so there will be a different voltage level between the 2 generator, so 2 machine. So we will supply each other lah. And the angle also have to be equal. If not, you will have a hair wire and phase A, and meanwhile you have the second motor or second generator with phase other than A, so it will supply each other. Instead of it combines the power, supply the grid, it will supply each other. And the frequency also have to be at the same. And the incoming frequency must be higher, because you tap to the load, for sure your shaft will be stuck or will be dragged a little bit, and you free running, then you put load, for sure your speed will be reduced. So the incoming generator from no load to the tap load must have higher frequency, such that you are able to cater the load of the grid at the time. So the frequency must be slightly higher than the frequency of the running system. And if not, when we connect together, the power transient will occur until generator stabilize at common frequency. Okay, you can read the steps here, how the synchronization takes place when we assume that generator 1 is supplying energy to the bus. So the incoming machine of genset 2 to be synchronized with alternator for the first time. and this is the genset 1 already connect to the load. Before genset 2 comes in, you have to increase the speed, and speed of the genset 2 adjusted until it turns to the value required to give a desired frequency. So the voltage of your genset 2 adjusted by means of their field rheostat. Means that their field current VF and field current circuit. Adjust the circuit until the voltage equal to the genset 1 here. Then the 3 voltage of the incoming generator must be in phase. We set them at the correct voltage and correct phase. And the phase sequence ABC have to be at the same sequence. And make sure the frequency is slightly higher. And use the synchronizing lamp to check their relationships. Then only you can tap in to the load or to the grid. Ready grid. So the active and reactive power of a generator. In terms of mathematical equation, the speed drop is considered as your no load speed minus your full load speed. No load speed, for sure you have a higher speed, minus your the reduced speed at your full load. So divide by your full load. So it's just like for other machine, this is your speed regulation. But in terms of synchronous motor or generator, we consider as, or we name it as speed drop. And or in terms of frequency, we can consider as frequency at no load minus frequency at full load divided by the full load frequency. So the speed drop usually in range of 2 to 5%. And so this is considered as a acceptable performance of your synchronous generator, 2 to 5%. Like your induction machine, also around 5%. And see, and all prime movers tend to behave similar, and which when the power draw from the system increase, the speed will decrease. And so to improve this, we have to use a governor which is connected to the prime mover. This one will control in terms of your speed drop or speed drop here. It used to maintain the stability of the generator speed by reducing the speed drop characteristic when the load is increased. So we use governor. So the speed drop, you have to take note how to calculate from the system. So this is the graph of the speed drop in terms of your speed. You increase your power from 0 to full load, and so your speed will drop. You increase your power from 0 to full load, power at full load, if you measure in terms of frequency, so you will see that the frequency in terms of rotation per minute and will also drop. So if the frequency of generated voltage is too low, frequency can be increased by increasing the no load speed of the mechanical governor. Means that if you found that the speed at this point is too low, so you have to shift all over the curve here. Means that the speed at no load here you have to increase. So you have the same trend here, same ramp or same kecerunan, but at the higher range. And the no load speed here increase a little bit, such that the end full load speed will be at the point that you need, or at the frequency that we expect the machine to behave. Okay, we expect it to be maybe around, if our frequency 50 Hz, so maybe the full load maybe at 50 Hz. So let's say if you run at full load, the frequency is less than 50 Hz, so we shift all together the graph here upwards. So we shift the graph. Okay. So active and reactive power of the generator. and see you in the next.